So this is the diffusion chapter that I had audio messed up for. But this will be diffusion, flux at the end. Hopefully I can redeem myself with this session. But diffusion, as you've probably kind of like reviewed from like chemistry and biology, is just simply a process of molecular motion, right? So it's when molecules will move from an area of high concentration to an area of low concentration, right? So from regions where molecules are highly concentrated to regions where they're not as concentrated, right? And so during diffusion, right, or at least not during diffusion, but like if you have those molecules moving, right, they'll undergo different random collisions with other particles in the room. So if you have, for example, if you're smoking, right, in this example here, then those gas particles from the smoke will interact and collide with other particles in the room as it kind of diffuses throughout the room. So yeah, random collisions is very important for this chapter, and that's something we're going to go over. But other than that, I think that's about it, what I want to cover for this slide. Particles in a vacuum at rest. Yeah.
The idea of, I think going on to the next slide, the idea of random collisions leads us to this random model walk. I think it's on the next slide.
Yeah.
So yeah, basically, on average, right? So note again, diffusion is a probability-based phenomenon, right? It's on average, molecules are going to move from high concentration to low concentration. If a question asked you about any one particle, you wouldn't be able to conclude anything about that single particle. So again, note, right? On average, all of our particles are going to move from high to low concentration, but each one on its own is going to be a random phenomenon.
Yep, individual will be random. On average, they go from high to low. So yeah, there's a couple problems as well that they'll ask you, for example, like if they'll have like a bunch of molecules located on the left and very little on the right. So they'll say like, okay, where is this molecule likely to move or something like that? Well, you can't be sure, right? But you're sure about that group of molecules, those group of particles that over time, right, on average, they'll move from left to right, from highly concentrated to low concentration. Otherwise, you can't necessarily say that, or define, I guess, where one particle will move left or right on its own. You can only define it by the average, right? The total collective motion of the particles. So this is a simple random walk model. There's a couple different conditions to this simple random walk model. So first of all, at t equals 0, they all start at the origin at a specific center point, right? Is where all the particles start off at. And then for every time step, right, this time step, it could be what? It could be 1 second, 2 seconds, whatever. It's just, yeah, it's just, yeah, one time interval essentially is the better way to say it. Yeah, so instead of time step, like think time interval. It could be 2 seconds, 3 seconds, 10 seconds, 1 second, whatever. And then for every time step, right, or every time interval, a molecule will move left to right a specific distance, and this is known as step size. This little here is step size, right? So for every time interval, the molecules will move a step size to the left or step size to the right. And that step size, once again, like the time intervals, it could be 10 meters, it could be 10 micrometers, 1 micrometer, whatever it is. It's just a specific like step size, right? And so stepping left or right in a simple random walk model happens with equal probability. So you have a 50% chance of moving left, 50% chance of moving right. So there's an equally likely probability of moving left to right with every time step, right? And then another really important concept to understand is that the step of any individual molecule is not affected by another, right? So just because, let's say you bumped into another particle, right? So one particle bumps into another particle. The step of that particle, that first particle, for example, is then not dependent just based on that collision, right? So any time step, there will be an equally likely probability of moving left or right? But if you were to have a particle collide with another particle, for example, or something else were to happen to that original particle, whether it moves left or right is not dependent on its interactions with other particles. It's only independent. It's not dependent on anything else, right? And then the final thing is that the speed of the particle, just like you have speed is x over t, right? It's the step size divided by the step, or the time step, right? So your time interval there. So that's the speed of the particle there.
You might hear those terms referred to as delta and tau. So delta
Yep.
again is just the step size, tau is time interval. So.
So quick check problem here says we start with 2 particles at the origin undergoing 1D random walk. What is the probability that 1 particle goes left and that 1 goes right on the first time step? So let's say you have those 2 particles, right? You either have, it's like flipping a coin. You either have heads or tails. Those are your 2 types of outcomes. So in this case, you could either go left or right. So with that probability chapter, like I said, it's the number of outcomes that you can have, heads or tails, A, T, G, and C if you're doing DNA, left to right with a random walk, right? Left to right is 2 outcomes raised to the number of like steps that you have, for example. So in this case, you're looking for 2 particles. And so instead of saying like raised to the number of steps, it would be raised to the number of particles, for example, as if you were flipping number of coins, right? So you have 2 particles that you're looking at, 2 outcomes for each particle there. So 2 raised to the power of 2, that gives you 4 total outcomes of different step combinations that you could have. So best way to do it is just write them out. Left, 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 right, right, left, right, right. So in this case, you're just looking for what is the probability that 1 goes left, 1 goes right. So in this case, you have LR and RL. 1 goes left, 1 goes right. 1 goes left, 1 goes right. So in that case, 2 out of your 4 outcomes will have that condition and satisfy that condition. Now, as we stated with the last chapter with probability, the idea for probability is that it's run over an extended period of trials with a large number of molecules, et cetera, right? So we won't see necessarily all the time 50% chance of flipping or getting heads or tails right within like 10 flips of a coin. You might get 10 heads in a row. You might get 3 heads, 7 tails, whatever, right? But the idea here is that over an extended period of time, that probability will kind of equate and equilibrate, right, and basically come to a standstill where it's about 50% with an infinite number of trials or a large number of molecules, right? So for that simple random walk model, right, you have, for that experiment, you have 2 inputs, number of particles and the number of time steps. So that's what I was talking about. You can either run that experiment with a large number of particles to where with that large number of particles, you're going to see that probability occur over time, or with a large number of time steps, right? So with an extended period of time, you should see a specific probability. So this right here, NP is 1001, so that's number of trials, right? And I think that's just I think that would just be the number of like particles, right? Yeah, number of particles. So they gave us 1001 particles. And then they ran the experiment for 4 different number of time steps, right? So these are images of the histograms with those different number of trials. So they kept the number of particles constant, but they increased the amount of time spent, right, as they observed this experiment going on. So as you can see, and we'll get into this with more detail here in a sec, but generally, it's most probable that the particles will end up where they started, on average, right? With an extended period of time, as you go from 15 to 30, 30 to 45, 45 to 60, right? When you give them more time to move, or we think about particles moving, if there's more opportunity, if there's more chance for the particles to move, then that means that they're going to move over time, right? But in every single case, you can see that in the middle here, on average, they're most likely to end up where they started. However, you notice that as you spend more time, as you give them more time to move, look at negative 15 and positive 15 here. You don't really see any values for those. After 30 time steps, maybe. After 45, okay, you start seeing a little bit more. So they'll kind of start to move outwards, right? As you spend more time and you give them more time to move, they're going to tend to move more outwards, but on average still, in every single distribution, you're going to see that they're most likely to end up where they started. Do they end up moving outwards more over time? Yes. They get more spread out. In a sense, your standard deviation would increase, right? You get more spread, more width to the distribution, but still on average, they end up where they started. So basic shape, like we said, is always the same. It's kind of that bell curve, right? Where you have spike in the middle there where you see you're most likely to end up where you started, and then some width there on the end. So if I have, maybe for the first one, right, you can see that this bell curve is kind of concentrated in the middle. With more time steps, things get more spread out, right? So, like I said, most likely result is that a particle ends where it starts, and then the farther away from the starting point, the less likely a molecule makes it there. So most likely to be in the middle here where it starts, start of the origin. And then as you increase in your time steps, it gets more and more likely for them to be found outwards, but still less likely on average overall to be found there compared to where they started. Does that make sense? Okay, so let's see here. So for this slide, analyzing probabilities, first fix a number of time steps. In each step, a particle can go left or right with equal probability, like we said before. So let's see here.
We're flipping a coin 3 times, right?
I think so, yeah.
If we flip a coin 3 times,
well, I think it's just is it a random walk or coin flip?
this is a random one. I think the next step might be a coin flip, but same process, right?
Yeah.
So I guess we can talk about this in the context of random walk. So if we have 3 separate time steps tau, it can either end up at -3 delta if it goes left, 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 +3 delta if it goes right, 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 or it can go 2 right, 1 left in any combination, in which case it would end up at either positive delta or negative delta. And again, there's 8 total outcomes, and we have to, I think we'll talk a little bit about the probability in the next slide, but again, this is just showing you with 3 separate time steps what the different outcomes are.
And that'll be like last time as well. You have your outcomes are left or right, heads or tails, right? And you have 3 like time steps that you're looking at, right? So 2 to the 3, that gives you to 8 total outcomes. Yeah, they said it's identical to a coin flip, so that's good.
I think, yeah, this slide
Yeah.
actually shows the coin flip. So, right, so 3 lefts and -3 delta, any combinations of 2 rights and 1 left, or 2 lefts and 1 right is either positive or negative delta, and 3 rights is going to be +2 delta. And so if we draw out our histogram, which it probably will not ask you to draw out a histogram from scratch, you'll again notice that most of our particles or most of our outcomes are going to be centered around 0, back to where they started, right? And we see, obviously, if we increase this to 5, 6, 7 trials, this graph is going to spread out wider and wider. But again, the peak should always still be right at the center.
So, and that's another thing that's important too. So with a simple random walk, if they were to tell you that the problem, like the condition, is a simple random walk, then you know that on average the particles are likely to end up back where they started, specifically at x equals 0. If it's a simple random walk model. However, right, if they didn't tell you it's a simple random walk model, there's a couple different ways you can go about figuring out where they would end up most likely. So the idea here is that if you didn't have a simple random walk model, if they didn't say that specifically, once again, you kind of go back to these 2 conditions. You'd either have to have a large number of particles or a large number of time steps, or both, basically, right? In that case, you would be approaching kind of that idea of a simple random walk model, an idea of like an infinite number of trials. And so then over time, or with a large number of particles, you would see on average that they would end up where they started, back at 0. But if they didn't state that, right, that's how you'd figure it out, that they would end up back at 0, or on average they would most likely end up back at 0 if the number of particles was really high or the number of time steps was really high. So if they said like 2 million particles or something, right, and let's say they ran it for, I don't know, 24 hours or something like that, right, then that's a large amount of time, or great amount of time to run that experiment. In that case, you might be able to approximate the distance or the position that they end up at, most likely as being 0. However, if you don't have those conditions, if there's not a lot of time steps, there's not a lot of particles, and they didn't say that there's simple random walk, then you cannot assume that the average position, or like the most likely position that they end up back at, is at 0. What you can do is that you can say that it's very close to 0. So if they say option A is like 40, right? You're 40 meters away. Option B is 0 meters away. Option C is 1 meter away, and option D is 5 meters away. Which do you think is the most likely position to end up at if they told you that it's not a simple random walk model? C, right? Because 0 is if it was a simple random walk model. 1 is the closest, it's the best option, it's the next best thing that you can get to. Because yes, regardless of what happens, they're most likely to end up back where they started, but only with the conditions of a simple random walk model, or with a large number of particles, or with a large number of time steps, can we specifically assume that you end up most likely at 0. Otherwise, if it's a small number of particles, small number of time steps, and they didn't say it's a simple random walk model, then we go with the next best thing, the closest thing. So 1 meter away, or 1 micrometer away, or whatever the value is, as long as it's pretty close to 0, then that's the best option that you have. And so you can see here, for example, this is a case where you wouldn't be able to say it's 0 because 0 isn't even an option. So your next best thing would be to say that it's 1 step size away, right? Whatever that step size is. Otherwise, as you can see here, with a greater number of time steps, if we go from 1 to 2 to 4, well then all of a sudden at 2, 0 pops up. At 4, 0 is there as well. And so you can see that they're more spread out here from 2 time steps to 4 time steps. You get particles that will be found at 2 step sizes away. And then in 4 time steps, you get particles that we found 4 step sizes away. But on average, the more you run the particle, the more you run the experiments and stuff, you're still going to find, on average, the greatest probability or greatest position, right? Or I don't know how I'm messing this up. The position with the greatest probability to find those particles at is always going to be back where they started at 0, given it's a simple random walk model or those 2 other conditions that I was talking about. Now, as you can see, still the greatest, but they've spread out a little bit more. See? So you have now additional bars. There's more width, more spread to the distribution, but on average, you end up back where you started. That's the most likely position there. Now, this is another example. So start with a particle at origin. What is the probability that after 4 time steps, it ends up back where it begins? So if we have 4 time steps, that's like 4 flips of a coin, right? So you have 2 outcomes, left or right, heads or tails, once again. You raise to the number of time steps, number of flips of a coin, for example. That gives us 16 total outcomes, right? Then you want to figure out, oh man, you want to continue because I'm done.
Yeah, once you get 16 total outcomes, it probably wouldn't be in your best interest of time to write out all 16 outcomes. What you should instead recognize is write out only the outcomes that the question is asking you to do. What is the probability that it ends up back where it begins? Well, if we have 4 time steps, the only way that can happen is if we have some combination of 2 rights and 2 lefts. And so those 2 rights and 2 lefts can alternate in any one of these various positions. And you just want to start off 2 lefts, 2 rights. Then you want to switch them off. And you just want to keep going through all of the different combinations that we can have 2 lefts and 2 rights. And these are 6 of the total outcomes out of the 16 that leads us back to our starting point.
And then with simple random walk model, once again, your step size is probably going to be 1, like 1 meter, 1 micrometer, whatever the units is. So you can see here that this would be like +1, or not, that's left, my bad. So -1, right? And then +1, +1. And so then you can see that'll cancel out and you end up where you started at, which is, that'll be 6 out of 16 outcomes. And so the simplest way is just to write them out, honestly. Like, I doubt that they'll give you a lot of time steps, for example, to run it for, because then it's not efficient.
And if you got that question right?
Yeah.
This next question asks us, what is the probability that it ends up 2 steps to the right of where it started? Well, we just found out 6 out of 16 is right in the middle, which hypothetically in a random walk model should be the point where we find the highest probability. So our only possible answer for this, given the answer choices, has to be the answer less than 6 out of 16.
Yeah, that's excellent.
If you wanted to, you could definitely write out the outcomes that leads us to 2 steps to the right. So that would be any combination of 3 rights and 1 left. So you just want to switch the position of the left in each of the 4 time steps. But if you got the previous column effortlessly, then this column should be easy.
Yep. Yeah, that's excellent actually too, because that's a really important way to think on the exam as well. Because like you could very well just write out the outcomes, and it might take you a while. Especially like say, so if they used basically the exact same kind of conditions, and you just did 2 to the 4, that's 16, and then you wrote out all these outcomes. That might be an extra minute that you spend, extra 2 minutes that you spend on the exam, when you can realize that, like Amit said, if you have at the beginning, it's 6 out of 16 that they're most likely to end up where they began. If that's your probability, then you know, if you understand the idea of a simple random walk model, ending up back where you started should have the highest probability in the entire distribution. So if you say it ends up 2 steps to the right, anywhere else, any other position has to be a lower probability. So that automatically eliminates 8 out of 16, 12, and 16 out of 16, because those would be higher probabilities. At the same time, for 6 out of 16, 6 out of 16 is already the probability that it ends up back where it started, and so 4 out of 16, like you said, would be the only option there. That's just some test-taking kind of knowledge there.
Notice that if that previous question said 2 steps away from where it started, you have to consider both positive 2 delta and negative 2 delta. So just be on alert mode in terms of what the question is.
Yeah. Because that in that case, actually, if it's 2 steps from where it started, right, then that would be 8 out of 16 in that case, right? And that would actually be a combined total probability that would be greater than where it started. So in this case, they only said 2 steps to the right, so that's actually an excellent example there.
It's just showing analysis versus experimental on basically the same.
Yeah. Let's see here, average final position after a random walk. So yes, the graph is symmetric. In the ideal case, the average is 0. In any real trial with a finite number of particles, like I said, finite number of particles, the average will be close to 0, but not exactly. So if they say, or if they don't say that it's a simple random walk model, and you have a finite number of particles, not an infinite or not a really large amount, then it's not exactly 0, but it's very close to 0, right? So that's the example that I gave earlier where I said if you had like 20 meters, 0, 1, and 5, then 1 would be your next best option because it's not a simple random walk model, or we don't have like a finite, or we don't have an infinite number of particles or a great number of particles or time steps. So it'll be close to 0, but not exactly. Now, here's where we get to average distance away from location, right? So average number of steps away, total distance is not 0. So this is the total distance ignoring the sign. And by ignoring the sign, that means, like Amit said earlier, you have step sizes to the left and step sizes to the right. So you can see here, since the probability distribution is kind of a bell curve, right? And that it's an equally likely or equal probability chance that you can move left or right, then you should see that moving 1 step size to the left should have the same probability roughly as moving 1 step size to the right. So if you were to find out like the average and stuff, then for a simple random walk model, it would make sense for it to be 0, right? Because if you just remember for the probability chapter, we did x, like the values, right, times the probabilities, and then we found the sum of that, right? So if we were to add up all those values, like we had 1 times the probability, say that's 0.1, and then step size to the left, -1 times, 1 times 0.10 plus -1 times 0.10, to where step size to the right and step size to the left have the exact same probability, then you can see that these will cancel out. If you do that same thing for every single step size, you'll realize that the average is 0. So average number of steps away, right, ignoring sign is not 0. But instead of saying like the average of like absolute value, we can just do a better measurement here, and that's using the XRMS distance away to figure out the actual like average number of steps away from the center, right? So that XRMS from the previous chapter, right, is that square root of the value squared and the average of those values. So the exponent with the inside on the brackets, right? And that's also equal to the square root of 2 dt, where d is your diffusion constant and t is your time. This isn't time steps, it's just time, right? So if they gave you like 16 seconds, that's 16 seconds is the time that you use here. Now the diffusion constant, right, that's equal to your step size squared divided by 2 times your time step, right? To where that, if you were to plug this in here, right, over 2 tau, right, times t, where t, what do I want to say?
Yeah, this t and that, so this t and that t are 2 different things, so just keep that.
Yeah, that's time between collisions. This tau right here is the time between collisions. But this time is the like diffusion time, basically, so the amount of time it takes for the particles as a collective effort to kind of diffuse. But what do I want to say? Because they should cancel out in a way. This tau, yeah, they should. There's a way for them to cancel out. I just can't remember what it is. So, oh no, okay, never mind.
So as long as you know those 2 equations.
Yeah, as long as you know those equations, you're good.
It's important to realize this is only for 1D motion. We'll cover 2D and 3D here in a little bit. Sometimes they will give you these 2 in separate units where they don't cancel out. So again, another thing you want to make sure you convert them to the same units, because the denominator of the diffusion constant and the time units for time should cancel out.
Yep.
We can go to the next slide.
And this is, once again, this is the average speed of a particle as it moves around. So the step size divided by the time step. And yeah, over time, particles will spread and diffuse. Individual particles are equally likely to move in one direction or another. But then looking at a collection of particles, they will most likely spread out over time. So over time, they'll spread out. Most likely end up back where they started, though, if it's a simple random walk. Yeah, we can skip this stuff here. And it's kind of the same reiteration once again that as you increase the time steps, as time passes, particles are more likely to spread out and be farther from the origin. But average position at any time, right, average is equal to 0. Most likely for a place for a particle to end up is near the origin, if it's a simple random walk model, right? Yeah, exactly. And then this is, review again. Yeah, and diffusion constant, the SI units are like meters squared per second, like distance squared per second, basically. Do you want to go over this problem?
So here, we're told that it's 1D motion, so we're able to use the formulas that we just learned. On the formula sheet, do they tell you whether it's 1D, 2D, or 3D? Like which formula?
They'll label out which formula for each one, but then based on the context of the problem, you'll have to figure out which one to use. They'll either say it's 1D motion, or if it's any biological context, at all, if it's a membrane, like particles diffusing over a membrane, no, that's in 3D, because let's say this is your membrane, right? Then your particles could move like up and down in the extracellular matrix, left and right, or into and out of the membrane. And the same thing goes for like once you hit the membrane, right? Then you could just move left to right and stuff like that, right? So for a biological context, it's 3D motion or 3D diffusion, right? But otherwise, it's most likely going to be 1D. Very rarely do you ever see a 2D problem.
Yeah, so for this one, right? So we might think, right, right away, we're given a diffusion constant, we're given a time. We might think to use XRMS is equal to square root 2dt for 1D motion, right? So we do 2 times the diffusion constant times the time, we get our RMS. But again, XRMS is a measure of the average of all of our particles. Read again what the question is asking, right? How far away from the origin is this single molecule? And that's why our answer for this is going to be not possible to say, because on average, all of our particles are going to be this distance away from the origin or from the starting point, but we don't know anything about this single individual particle. So whenever, almost 90% of the time, if they ask me about something for a single molecule, it's, when dealing with probabilities and averages, it's going to be indeterminate or not possible.
Exactly. And that, you can think about it too as like if you have, if we just draw those particles out like after a certain time period, right? Let's say if this was like a board here that we have, so this is the origin, right? Let's say after a specific number of time steps, most of them end up here. This would be your this would essentially be your X RMS value, right? But let's say maybe there's one particle that stayed back here at the origin. Well, when they say how far away from the origin is this molecule, we don't know which molecule we're talking about, right? It could very well be this one. In that case, it would be 0, for example. Or, right, if once we calculate it, we can figure out what the distance is, right? But really, when you're calculating this XRMS, it's telling you on average, like, what's the position of all of the molecules when they move together as a collective effort, rather than one individual molecule alone. So that's why it's not possible to say. And that goes the same for time as well. So we can't figure out the time it takes for a single molecule to travel a distance. We can only figure out the average time it takes for them to diffuse.
This equation is basically just expanding, right? So we already know this formula from before. XRMS is equal to square root 2dt. We can simply square that to find one part of our standard deviation equation, right? So that's basically how all these topics are kind of interconnected, right? We square both sides. Here we got XRMS squared is equal to 2dt. And so that's what we get.
So your XRMS squared, that would give you your x squared with the exponents on the inside, and that's equal to 2dt.
You
Makes
might not
sense?
have seen this first part before. You might have seen as XRMS is equal to square root of this.
Yeah.
So that's basically how that came.
That's the original equation, and then if you square both sides, you get rid of the square root, and so then you're just left with x RMS squared is equal to x squared with the exponent on the inside, and then this is equal to 2dt. Right?
Any questions on that?
Nope. Same thing here, like this is once again just kind of reiteration and going back to the probability chapter as well. So like say you have that simple random walk model, right? Then we're assuming that the average is 0. So when we're looking at standard deviation, if we go back to the standard deviation equation, which is your average squared with the exponent on the inside minus your average squared with the exponent on the outside, if your average by itself is 0, then this is 0 squared. So remember what I said, if you have your average, if your average is 0, that's a condition, and that's, let's say that's your simple random walk condition, right? Because that's what it is. Then that means that your RMS distance, your RMS average, is actually the same as your standard deviation, because you'd just be left with this, right? We know that the XRMS is equal to this, and then just because of the fact that your average happens to be 0, just because it happens to be 0, your standard deviation happens to also equal your XRMS, right? So XRMS and your standard deviation would be equivalent ways of describing the spread or distribution that we see here for the diffusion, right? So as you increase in your XRMS, you can say that you're getting more spread out, the particles are moving outwards more, right? And that makes sense, because if they're collectively moving out more, then they're being more spread out, right? Same goes for standard deviation. As you increase in the standard deviation, right, you go from 2.2, 3.9, 6.78, you can see that the distribution gets more and more spread out over time, but you're still most likely to find the particles back where they started at 0. So you see here, like -10, we didn't have anything here. We have a little bit here and a lot more there, right? So they spread out more over time. The outer distances get more and more likely, but they'll never be as likely as the center. Does that make sense? They'll get more and more likely, but they'll never be as likely as the center. Let's see here. So this is particle undergoes a random walk in 1D. After 100 steps, where's the particle most likely to be? So undergoes a random walk. That's the condition there, right? So that tells us this is a simple random walk model. So about 0 steps from where it started is where it's most likely to be. Otherwise, if they didn't tell you it's a simple random walk model in 1D, then you can't really assume that it's 0. The next best thing would be 10, right?
So you can't actually identify where exactly the particle is, because it could be at 100 delta or -100 delta.
Mm-hmm.
But again, since it's only asking about the most likely, you know the most likely spot is back.
Exactly. So it's going by probability, basically, not telling you exactly where it is and stuff. A lot of random walkers start in 1D near 0 and step in random directions with equal probability. As time grows, how will the width, the standard deviation of the distribution of molecules change with time? So we know this is the condition, random walkers starting in 1D near 0, right? So that tells us that this is a simple random walk. Given that it's a simple random walk, what do we know about the average? I'm asking you guys, my bad, sorry. Since it's a simple random walk, the average would be what? Yep, exactly. So average is 0. So in a simple random walk, your average is 0. And then with regards to your standard deviation, right, because they're asking about width, and width is standard deviation. Standard deviation is square root of your squared values and the average of those values minus the average squared. If the average is 0, this is 0 squared, so you're left with standard dev is equal to square root of x squared, like that, right? We know this just so happens to be equal to what? XRMS, right? So if this is equal to XRMS, we know that XRMS is also equal to square root of 2dt. So if your standard deviation just so happens to be equal to your XRMS, because this is a simple random walk model, and the XRMS is equal to the square root of 2dt, then we know that the width will be dependent and will increase based on root 2dt. So that's why that's the answer there. And then this is just different conditions if you have 2D and 3D, how those equations will adjust. So we know for 1D, we would just have root 2dt. This is like a derivation for all of these. I don't think it's that important, but basically these are the equations you're going to use for 2D and 3D. 2D would be root 4dt, 3D would be root 6dt.
Now the RMS, this R is not necessarily the radius of
Yeah.
the circle or a sphere. It's just the total distance traversed.
Mm-hmm.
If it's easier for you to visualize it, just treat it as XRMS. But sometimes they'll trick you, they'll give you a radius or something, and then they'll ask you for the distance from end to end, in which case you have to take 2 times the radius to find the total distance.
Yep. But yeah. So yeah, this is the root mean squared distance, yeah. So this is like, once again, this is like your width of the diffusion, width of the distribution, because once again, if it's a simple random walk model, you end up most likely where you started, so that's 0. In that case, your standard deviation would just be equal to your RRMS. Yeah, T, this T right here is the diffusion time. it's a time for the distribution of all the molecules to reach that RRMS, right? So it's a total time to move as a collective effort to RRMS. But yeah, it's not the time it takes for any individual molecule to move that RRMS distance. So I don't know if they have an example like they told you, like, oh, particles diffuse 16 seconds or something like that. Like, where would one molecule end up? We can't really say because we're not sure about one molecule. All we know is about the collective effort, the collective movement of all of the molecules together. Yeah, these are different diffusion constants. We can skip that. Yeah, so in this simulation, a lot of walkers start in 2D near zero and step in a random direction with equal probability. As time grows, what will happen to the distribution of walkers? So we know that as we increase in time steps, the molecules will tend to move out, spread out more, because you're giving them the opportunity to move. So when you give them the opportunity to move, they're more likely than not to kind of move outwards, right? However, as they move outwards, right, the probability of them moving outwards to those outer distances is going to increase, but they'll never be as good as coming back to the center, right? So more will be at zero than anywhere else. They're more likely to end up at zero, back where they started, with the probability of finding them outwards decreasing, and the distribution gets wider and wider. So you can see here that that's the idea there, that you have a bell curve kind of distribution where more will be at zero than anywhere else. They're more likely to be here, right? And then the probability of finding them outwards is going to decrease over time. And so the distribution is going to get wider and wider. So if you increase number of time steps, you allow them to walk, they're going to be, the probability of finding them in those outer limits, those outer distances is going to increase, but it's never going to be as much as finding them in the center. So yeah, this is RRMS 3D. So if it says, if you're asked how long does it take for a molecule to diffuse a distance of x meters, you cannot just plug in x for RRMS there, because that's going to be the distance for one molecule. RRMS is the collective distance on average that all of the molecules move together with. So don't be tricked if they just tell you how long does it take t for a molecule, a single molecule, to move 10 meters. I can't just plug in 10 meters here and then solve for time. That's just one molecule. This RRMS strictly refers to the distance that those collective molecules move, right, on average. So, and it's also a measure of the width. Like we said, it's a measure of that standard deviation, because the nature of a simple random walk model is that you end up back where you started at x equals 0. So this RRMS just so happens to be equal to your standard dev, right? Yeah. So, and like I said, t is the diffusion time, measure of how long it takes for the particles to spread out over that specific RRMS distance. Just the example problem, I think, do I solve it here?
Yeah, let's go through this one over here.
Yeah.
So here, we're just comparing two separate times, one for a typical cell, one for the smallest mammals. We're given the diameters of both of them, and we're also given the diffusion constant of air, I believe, or oxygen molecules, and we just want to calculate the time that it takes to spread across the width, so across from one end to the other end. And so if you go down to the next slide, all we have to do is just plug in RRMS equals square root 60t for both the cell as well as the smallest mammals. The diffusion constant is going to be the same. 6 is just a constant here. This RRMS is going to be different, right? Because for the cell, it's going to be 10 micrometers. Note one small subtlety here. The diffusion constant is given in units of meters squared per second. That means we have to convert both of our distance units, both of our RMS units, to meters, right? To keep our units, to make sure our units cancel out at the end. And so, is the solution on the next slide?
I think so, yeah.
Yeah. So, what they did here, right? They isolated t. If you set up your equation, RRMS equals square root 60t, you'll find that t is equal to RRMS squared over 6d. Again, note the conversion between micrometers to meters. Square that divided by 6 times the diffusion constant. Same thing for the mammals, right? Conversion from millimeters to meters. Square that divided by 6d, and you'll get two separate diffusion times. So yeah.
I don't know if I wanted to say anything else here for the RRMS, but I think that's it for that specific problem. The only thing that I would add is, yeah, because nowhere did they say that this is 3D anywhere, but it's 3D because it's a cellular environment. So whenever you have a biological context, a cellular environment, you're going to use 3D equation there for that one. But I think that's it for those slides there. Time, okay. Yeah. Yeah. Okay, cool.
Any questions on anything so far?
And then we're going on to Brownian motion now, if all of you guys are all right. But so Brownian motion is just random motion of those particles that is caused by like a lot of random collisions, basically. So it's not only the particles interacting with themselves, but it's the particles interacting with the fluid that they're submerged in. Can you close the door? Yeah, but
probably don't need to know the definition of it, to be honest.
Yeah, just the concept. Yeah, I don't think it's going to be tested.
Next slide also has the same formula we just talked about.
Well, yeah, its average kinetic energy is 3/2 kBT. Yeah, collisions will raise temperature. So the more collisions that you have, it's going to raise the temperature. So it'll raise the temperature to a point where the particles will have the same average kinetic energy as the surrounding fluid, right? So it's Brownian motion is the result of random collisions with the fluid molecules. So let's say you have gas particles in a fluid, for example, right? Or water, for example, or another fluid, whatever. But it's not only just going to be the particles interacting with each other, colliding with each other, but also colliding with the other fluid molecules that it's submerged in. And so those collisions will cause the average kinetic energy of the molecule to be equal to the surrounding fluid. So that's the idea of Brownian motion there. And then here's an example problem. They're asking, consider a bacterium with a mass of 1 picogram, which is trying to sit still in water, which is at 300 Kelvin. And then due to Brownian motion, the bacterium will bounce around. What will its RMS speed be? So remember RMS speed, VRMS, in that original equation that we had, average kinetic energy is equal to, yeah, it has it up on the board, half mv. This is RMS squared. Well, there we go. Average kinetic energy is half m VRMS squared, and that's equal to 3/2 kBT. Now, we're trying to figure out what the RMS speed is, so we can just isolate for the variable here, right? And so we can just multiply over 2, divide over m. And remember what I said earlier, I think it's best to memorize this equation because, like I said, it's going to be used very frequently. So VRMS is equal to root 3 kBT over m, where m is your mass per particle. And that's going to be in kilograms per particle. And so, yeah. So I don't know what I did here with this stuff. I think I just wrote out the whole thing and then solved it like that. But essentially, these two will cancel out. So you're left with 3 times kb times t, and then divided by the mass there for the bacterium, and that gives you your RMS speed.
Again, don't forget to convert the mass to SI units.
Yeah.
They give it to you in picograms, but the SI units kilograms, for.
Yeah. SI units would be kilograms. So you go from picograms to kilograms to get that proper. And then this is the Einstein-Stokes equation, which is pretty much just used to find out your diffusion constant if it's not given to you. So it's based on this relationship here. So you have diffusion constant is dependent on the Boltzmann's constant times your temperature divided by 6 pi times your viscosity times your radius. And so, yeah, that's pretty much it. It says very useful except for when the temperature is fixed. You really don't have to know all these different conditions. It's, yeah, just know the formula, know how to use it. Yeah.
Definitely know if everything's held constant, increases in one variable, how they affect increases, or how they affect another variable.
And you can see here that from this relationship too, if they were to ask you something on a multiple choice question, for example, to kind of relate what's going on here. So you can see that as you increase your temperature, right, you're increasing your diffusion constant. So that will also in turn make it easier for the molecules to diffuse. If they're at a higher temperature, they're going to be moving faster and stuff because that will increase the average kinetic energy. And then if you were to increase viscosity, and remember viscosity is kind of a measure of the thickness of a fluid. If you were to increase viscosity, increase the denominator, it decreases the diffusion constant. So it makes it very hard to kind of move around, right? So In that sense, if they were to ask you like the relationships between the variables, then you know an increase in temperature will increase diffusion constant, increase XRMS, for example, as well, or RRMS.
I think there's a practice question on the next slide. Where they're comparing, so two spheres, right? One has a radius 4 times as big. Everything else is basically the same. And we're basically asking us how big is the size of the distribution. So this how big, like you might think of it as like standard deviation, or you might think of it as RRMS. Regardless, they have a one-to-one, like not one-to-one, but they have a direct proportionality relationship. So the only thing you really need to do here is compare how the diffusion constants are, like how the diffusion constants are related for the larger dust particles compared to the smaller dust particles. So the larger dust particles have a radius 4 times bigger. So does that mean they're going to have a diffusion constant that's 4 times bigger or 4 times smaller? Smaller, right? Because again, R is in the denominator, so increases in the denominator lead to decreases on the other side, basically. So our larger particles should have a smaller diffusion constant, right? That's the first
Yeah.
one. Yeah. And then we have to plug that into our RMS equation, which is equal to square root 60t. So I guess if you like working at it all at once, you know that, are you treating B as the...
Yeah, D as in like big particle and small is S as a small particle.
Yes. So the reason we get this relationship, right, is this tells us that the small particle has a diffusion constant that's 4 times as big as the big diffusion particle.
And that comes from like this area here. So I just plugged into the Einstein-Stokes equation, right? So I can see here that the dust particles, the big dust particles versus the small dust particles, the big dust particles have a radius 4 times bigger. So 4 times the radius, right? And then I can see here that if I compare dB to ds, right, big to small particles, then I can see that this big dust particle has 1/4, right? This is 1/4 times this part. This is the ds, right? So ds here is kBt over 6 pi viscosity times r. So this is the section here that's equivalent there. And so you can see here it's 1/4. So dB is 1/4 of ds. So that means also that the dust particle, the small dust particle has 4 times the diffusion constant size of the big dust particle. And so if they're asking about how big is the size of the distribution of the smaller dust particles, right, then I'm looking for the RRMS for the smaller dust particle, right? So for the smaller dust particle, ds, I want to set it up to where I can figure out what the diffusion constant is for that one, and that's 4 times the diffusion constant of the big dust particle. And the reason why we're saying that the distribution is RRMS once again is because the RRMS is equal to the standard deviation, because your average, the most likely position that you're going to end up at is back again at 0, right? Because this is a simple random walk model. So if we're doing RRMS equals the square root of 6 dst, well, ds is equal to 4 dB. So 6 times 4 dB times t, well, then we can see then that the size of the distribution, or the RRMS of the small dust particles, is actually 2 times the distribution of the larger one. Because we want to write, because this RRMS is for the smaller particles, we want to write it in terms of the bigger ones. So that way we can see that, okay, 6 times 4 dBt, this 4 is going to be pulled out of the square root. It'll just be 2 times square root dBt. dBt, the square root of 6 dBt, would normally give us the RRMS, or the the standard deviation of the bigger dust particle. But once we write it like this in terms to figure out the smaller dust particle, then we can see that it's 2 times the bigger dust particle's width or distribution. Does that make sense? I know it's kind of weird. Right? Yes? No?
You can almost guarantee one proportionality.
Yeah, definitely you're going to see one of these.
These kinds of questions, so.
And then this is just kind of a reiteration of Einstein-Stokes equation. And yeah, I think that's it for this one. Yeah. I think that's it for the Einstein-Stokes equation stuff. Oh, but this might be, I think this is an example problem. But I don't know. They didn't have that. Okay, so I'll forgo it for now. But now we're getting to diffusion and concentration with particle flux and Fick's law. So Fick's law is a statement concerning the rate of particle transfer, right? And the components that go into Fick's law are concentration and particle flux. So concentration, right, we're normally used to measuring it in like moles per liter for like our chemistry classes, our biology classes, whatnot. But in this case, we're defining it as the number of molecules divided by the volume of the region. So it's slightly different. It's not moles. It's going to be molecules this time. So molecules or ions or particles per volume, and that's going to be usually in meters cubed. That's your SI units there. So moles per meter cubed, or we'll do molecules per meter cubed. But I think, yeah, so apparently, yeah, the SI units are moles per meter cubed.
Yeah.
But a lot of the problems will do molecules or ions or particles per meter cubed. So you need to adjust for that.
Yeah, note that they're the same formula, just the
yeah.
units you have. So as long as you keep the units in check, then
But yeah.
both are acceptable answers.
And then, okay, so here's Fick's law. Particle flux J is a measure of the rate at which particles are moving. So how many moles or how many particles, right, per second. But at the same time, flux also factors in the area, right? So it's not just the measure of the rate at which particles are moving, but it's the rate at which particles are moving through a specific area, right? So it's like number of particles that are moving per second per gateway or per area, right? Or per membrane or something like that. So that's why the SI units here are moles per meter squared. Meter squared is your area times seconds here, right? And so for the particle flux equation, it's the concentration times your average velocity. What's that?
It's like an expanded version of it.
Oh, okay. Yeah, and one last thing is that the particle flux is denoted with positive or negative values, and that's going to be moving left or right or left in that sense. What did I say? Yeah. This is, particle flux once again, but then this is strictly the number of particles per unit of time without including the area. And then here you can see that the flux includes the area, as we said before, because the units would be like, it'd be saying the number of particles flowing per second per unit area. And then if you multiply the area, then the area was cancel out and you're just left with the number of particles moving through per second. So this would be like your particle flow, essentially.
Don't worry about the cosine theta stuff.
Yeah, the cosine theta is not going to be a huge issue. Is it necessary to kind of go over that?
0 or 180.
Yeah. But, and they got rid of it here, just show you that the flux times the area will give you the flow there for the particles, right? So, what does it say? Only component is flux, so the rate at which particles pass through the surface is this. This is the rate at which particles pass through the surface without respect to the area. When the rate is positive, that means particles are moving to the right. When the rate is negative, particles are moving to the left, right?
That's just convention, right? That's just something.
Yeah. Let's see here. So consider a surface with an area of 1 centimeter squared. Suppose that over a time interval of 1 nanosecond, 8 molecules from the left move across to the right, while at the same time 10 molecules from the right move across to the left. What is the particle flux? Do you want to go ahead?
Yeah. So first of all, we're dealing with flux, right? So we want to write out an equation for flux, which is n over delta t is equal to j sub x, indicating that's flux in the x direction, either positive or negative, we don't know yet, times the area. So you might think, well, so first of all, we're given the area in units of centimeters squared. So this is equal to area. So that's one thing to keep track of. We're also given a time interval of 1 nanosecond. So this is our delta t, which is our denominator. However, we're not explicitly given what this n value is. Instead, what we're given is the fact that 8 molecules move to the left, while at the same time, 8 molecules move to the right, while at the same time 10 molecules move to the left. And
Oh wait, I think it's the other way around. You had it first at the beginning. 8 molecules to the left and 10 molecules. Wait, hold up.
8 from the left to the right.
Wow, that's such a weird wording.
Yeah. So overall, we have 8 to the right, 10 to the left.
Yeah.
So overall, we're going to have 2 to the left. Remember again, left in flux denotes negative, right denotes positive. So our overall is going to be -2 molecules or 2 molecules to the left. But we indicated as -2, right? And so that's going to be our n value, right?
Mm-hmm.
Yeah, so this is going to be our n value. Then we have to divide this by delta t. But remember, luckily for us, actually we don't have to convert all of these units because if we note in our answer choices, all of our units for flux are given in centimeters squared times nanoseconds. We're given a centimeter squared here and nanoseconds here, so that indicates that we don't need to convert anything.
Yep.
So again, we do -2 for n divided by delta t, which is 1, is equal to j sub x times 1, and we get j sub x to be -2. So overall, we're going to be our answer C basically. Every
Yep.
2 molecules per centimeter squared.
Yep.
Any questions on that?
Nope. And then Fick's law in 1D motion, right? You have the flux is equal to the negative of the diffusion constant times your change in concentration over this would essentially be like the thickness of the membrane, right? I think that's usually what they have it as, right? Thickness of the membrane. So the negative sign says that particles will flow from high concentration to low concentration, and we assume that delta x is positive. So that's the thickness of the membrane. And then, so the way I kind of think about it is that like, if you're really highly concentrated here on the left, and you move to the right, you should see a positive flux. And if you're highly concentrated on the right here, and you move to the left to the lower concentration, because that's how diffusion works, you should see a negative flux that way, right? So as concentration gets smaller from left to right, you're moving to the right, so that's positive flux. As concentration gets bigger from right to left, well, you're moving this way, right? But the way I think about it is that, okay, well, if we're going by diffusion standards, that we're moving from high concentration to low concentration, then you start here and you move left to where you start from high concentration to low concentration. You're moving left, so you have a negative flux, right? So, and you can see here, like if we're going by the graphs, you should see an increase in concentration. So a positive concentration would be a negative flux to show that things are moving out, and then, or moving to the left. And then for this graph here, you should see a decrease in concentration. So a negative with another negative shows that it's moving to the right. So if you were just to draw, like this is your membrane, right? Here are the particles on the left, here are the particles on the right. If they're moving from the left to the right like this, there's a decrease of the particles on the left-hand side here, decrease in concentration. So this means a negative C. A negative with another negative means a positive flux. And that positive flux, positive or negative flux just means left or right. A positive flux means you're moving to the right. So I just think about particles moving from left to right across this membrane, giving that there's high concentration over here and low concentration over there, right? If I think about this side right here, then I think about, okay, well, here's right, here's left. I'm more concentrated on the right, I'm less concentrated on the left. So based on diffusion, I go from right to left, moving left this way, right? And so if I move from high concentration to low concentration this way, right, as diffusion goes, that's how I can determine my flux direction, because that'll just be moving to the left. Now, how does that kind of translate to what happens with my concentration? Well, as I go from right to left, well actually, I take that back. Usually I think the graph here is looking at the concentration on the left-hand side of the membrane. So if you're lowly concentrated on the left-hand side, you should see a small concentration on the left, right? So this is left, this is right, basically. So if I see low concentration on the left, high concentration on the right, then I'm gonna move from high concentration to low concentration, right? So that gives me a flux that is negative, but at the same time, that's because I see an increase in concentration on my left. If I see an increase in concentration, that gives me a positive C value, and that gives me a negative flux. Do you see how that works there? Does that make sense? And let's see here. So this is all about the flux again with thickness of the membrane. So says consider diffusion of oxygen to a cell across the cell membrane. What changes in the thickness or area of the cell would change the particle flux? So the particle flux would just be affected by the thickness of the membrane, looking at this equation strictly here. So if you change the thickness of the membrane, if you increase or decrease, you're going to change the flux. Then it asks what changes in thickness or area would change the net flow of particles across the boundary. In that case, both thickness and area would affect the net flow of particles, right? So if I'm looking at the net flow of particles, where that was up there, yeah, right? So net flow of particles, this is the net flow. It's affected by the area. So if I increase or decrease area, that will affect my net flow of particles. At the same time, if I look at what flux is, if I expand this equation, right, to be negative d delta c over delta x, then by extension, any changes that would cause a change in flux would also cause a change in my net flow. Because if you think about it, flux is just the same as flow, but it's flow through a specific area, right? So if I see a change in thickness of membrane, it would affect the flux. It would also affect the net flow. If I see a change in my diffusion constant or a change in my concentration, that should also affect the net flow. And same thing for area here. So the three factors then that would change the net flow would be thickness of membrane, flux changing, or obviously like the flow of particles there, changing N over T by itself. And then if oxygen is flowing into the cell via diffusion alone, is what can we say about how the concentration of oxygen compares inside the cell versus outside it? So if you're moving, if oxygen is moving inside the cell, then oxygen was lowly concentrated inside the cell, right? So if we wanted to say like, and obviously how diffusion works is high to low concentration, so it flows inside the cell. So if you were to just set up things as left and right, so if you were to just say like this is your membrane, here's inside the cell, here's outside, which is kind of pretty much convention almost. You always have your inside is on the left for the most part with a lot of these problems, or at least that's how I think about it. But in that case, if oxygen is flowing inside the cell, then the flow is to the left. If the flow is to the left, flux is negative. Because you're increasing concentration. If delta C goes up, you're left with that negative sign there. And so, yeah, in that case, your flux would be negative because you're moving inside the cell to the left. So I think for at least these types of problems, I would always think about your inside being on the left, your outside being on the right. And then that's whether it moves right or left for the molecules will determine if you have a positive or negative flux. And then this is just kind of a reiteration of like all of these different concepts that we go over with probability and stuff that you can't be necessarily sure about one individual molecule or one individual particle. So it says a small patch of the cell membrane is shown yellow. There are more ions on the left than on the right. What do you expect is true about the ions on the left side? So you might think, okay, well, there's more particles here, so high to low, that the particles will move to the right. So you'd think that more ions go to the right because it's moving from high concentration to low concentration. But in reality, it's an equal number of ions move to the right, equal to the left, right? Because we can imagine this is kind of like a simple random walk almost, right, with diffusion. But the idea here is that we can't necessarily like say or determine like what's going on for one molecule, right? Or even just this group of molecules. We can only kind of say like on average how they move as a collective effort. And that'll be kind of reaffirmed here in not this example, but the next one. But this one is kind of the same here as well. Like if you have fewer molecules here on the right, it says, what do you expect for the ions on the right side? Well, once again, it would be equal number move right, equal number move left. As with a simple random walk model, there's an equal chance of moving left or right. But with this example here, they said there are more ions on the left than on the right. If the membrane allows ions to pass through, what do you expect will be true? So there should be a net flow of ions to the right. That is, if there are more ions, if they specifically say there's more ions, right? And then if the membrane allows the ions to pass through. So if the membrane is allowing ions to pass through, then you expect that collective motion to be towards the right. Otherwise, for these problems, they're just telling you that there's more on one side than another, and then really they're not telling you that the membrane is allowing for the motion of all of the particles to go. So
Really, it's a difference between probability, like two separate outcomes, whereas this is you cannot treat it as a net flow. So flux is all about net flow. All the molecules in our system, but we're never able to conclude anything about any individual molecule or set of molecules.
Yep. And then these two examples here about like flux again, but I think
it would be more beneficial
to go through the practice slides. But I think that's it for this review session. So for those that are be watching this online on YouTube, sorry about messing up the recording last time. This is redemption for that. So you guys will have access to that. I'll upload it. I'll try to upload it here. If not, then I'll go home and I'll upload it then. But that'll be the a replacement for the quiz review, or at least I'll like upload this in addition to that, because that one also I went over the quiz, so I haven't went over the quiz here. But yeah, that's it for this review, and then we'll go over some practice problems from the exam now in a sec. But yeah, thanks.